This is Tom Lin. I'm with NSPO, and currently I'm Program Manager of Triton Mission. And I'm very happy to host this section this morning. This morning we have 4 presenters, and the first one is from Professor Chris Ruf. His topic is CYGNSS mission overview. And now we start the first presentation.
Good morning, and thank you for inviting me to present at the TSU PRISMS seminar series. My name is Chris Ruf. I'm the principal investigator of the NASA Cygnus mission and a professor of climate and space sciences and engineering at the University of Michigan in the United States. Cygnus was originally conceived as a mission to monitor ocean winds, in particular ocean winds in tropical cyclones. Some of the driving properties of the cyclone measurements that drove our mission design architecture were the ability to measure winds under heavy precipitation and the ability to measure winds often enough to be able to resolve short timescale processes such as rapid intensification. The design of the mission that followed from those requirements was flying 8 satellites in a common orbit so that we could have better temporal sampling. The orbit inclination was chosen as 35 degrees so that we spent all of our time over the latitude zones where tropical cyclones are most common, and we use the GPS GNSS-R bistatic radar measurement technique in order to get adequate penetration through the heavy precipitation. The mission timeline, we started the mission concept design in December 2012. That was phase A of the mission. And then we designed the satellites and the science algorithms, built the satellites, tested them, and launched in December of 2016. The first 3 months on orbit were spent in engineering commissioning, the tail end of phase D, and then in March 2017 we started phase E, which is the science phase of the mission, and we've been in phase E since then. This is a pictorial illustration of the GNSS-R concept, which I think you're all familiar with. GPS transmits all the time to do its navigation function. The scattered signal from the surface goes back up into space, and then the Cygnus receivers receive the scattered signal. We're able to geolocate the scattering signal because of 2 properties. One of them is the propagation time of the signal, and these ellipses are ISO delay lines that have common propagation times. The specular point, where most of the scattered signal comes from, has the property that it has the minimum propagation time, and then higher propagation times expand out around that. And then the other dimension is the Doppler shift. These hyperbolae here are ISO Doppler lines, so by filtering by propagation time or range gating and by Doppler shift with Doppler filters, we're able to geolocate different parts of the signal. A few pictures of the hardware as it was being fabricated. Here's one of the flight satellites going through electrical functional testing on the bench. Here are 4 of the satellites going into a thermal vacuum test, and this figure on the right here, you can also see one of the science antennas. That's this yellow rectangle here. It's a 2x3 phased array. It's as large as it is in order to get adequate signal to noise for the reflected signals. And then finally, this is one of the satellites with its solar panels fully deployed, doing solar panel deployment testing.
LC, PLT, copy.
This is a video that was made on the day of launch.
PLT, LC is go for launch. PLT confirm.
LC, PLT confirms go for launch.
Drop on my mark. 3,
2, 1. Go for release.
Pegasus is away.
And drop. Pegasus is away. mission of the Pegasus rocket was Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
Fin actuator system is working properly to control the flight of the vehicle during stage 1. Power buses remain nominal, approximately 30 seconds into flight.
RCO. First motion ignition, first motion time of 13:37:21.
Vehicle is now past max Q. Attitude remains
That's
nominal.
13:37:21
30 seconds until stage 1 burnout. Attitude remains nominal. Power buses remain strong.
All data coming back.
Approximately 10 seconds until stage 1 burnout.
All data coming back looks good. Getting ready for the first stage to burn out. Right on time.
Stage 1 is burned out. Attitude remains nominal.
So after launch, we were in orbit about 14 minutes later, and then the 8 satellites were deployed from the 3rd stage of the rocket, and this is an illustration of that deployment maneuver. The satellites were deployed in pairs, and immediately after deployment, the solar panels opened up, the batteries were recharged, and then we started communicating with the individual satellites and started the 3-month engineering commissioning phase. This is an illustration of how our sampling works. So each one of the satellites has 2 science antennas, and these are the antenna patterns projected down onto the ground. When a specular point reflection enters the antenna pattern, the onboard processor acquires it with the Doppler filters and the range gating filters and the PRN correlation sequence. We have enough onboard processing power to track 4 specular points at a time in parallel. So we choose the specular points that have the highest antenna gain in the patterns and track those as they pass through the antenna pattern. And this shows you pictorially how those samples work. So as a specular point is tracked, we get these specular point tracks. There's 8 satellites, each one tracking 4 reflections. So the composite of all 32 of those simultaneous reflections builds up our coverage. And this shows you how the coverage builds up over time. This also illustrates the 35-degree latitude orbit inclination and our resulting coverage. And then this is another picture of the coverage. The top image is the coverage over 1 orbit, and the bottom is the coverage over 24 hours. These are examples of some of the wind products that we measured over 1 day, over one 24-hour period. On the right is a 24-hour period of overpasses of Typhoon Goni from last year. And then on the lower left is the global coverage product over a typical day. And again, these are the measurements made by all 8 satellites composited together. In terms of the data products that are produced by the mission, there's a number of different levels of products. The level 1 product is our engineering data product. That's the scattering cross-section of the ocean surface, and it's appropriate for incoherent scattering from rough surfaces over smooth surfaces, and in particular over inland water bodies. Scattering cross-section isn't really the appropriate engineering parameter. It's reflectivity, and so we also produce a reflectivity level 1 data product appropriate for coherent scattering from smooth surfaces. Level 2 products are derived from the level 1 products. Over the ocean, we have a ocean surface roughness product, in particular the mean square slope statistic of the ocean surface, and also a near surface wind speed, reference to 10 meters, and neutral atmospheric stability conditions. There are also 2 ocean surface heat flux products, both latent and sensible heat. And then there are level 3 gridded versions of all of the level 2 products, the winds, the mean square slope, and the heat fluxes. There's also a level 3 gridded product for soil moisture, 2 of them. One of them is a 6-hourly product and the other is a daily product. These soil moisture products are derived from the level 1 reflectivity product Overland. And then finally, there's a level 3 6-hourly tropical cyclone overpass product. And in this case, because it's gridded over a 6-hour period of time, we use relative storm-centric coordinates to re-register all of the samples within a 6-hour window. Because over 6 hours, very often the storm moves enough that you get some blurring of the storm structure if you don't use relative storm-centric coordinates. So these are all the data products that are now routinely produced by the mission, and these are all publicly available on the NASA PODAC website. One detail about the level 1 calibration that I wanted to point out to you, since you'll be calibrating your data soon, and it has to do with the variability of the transmit power level of the GPS navigation satellites. We track the strength of the GPS signal, the direct signal, using the navigation receiver that's on the top of the Cygnus satellite. There's also science receivers and science antennas on the bottom of the satellite that are looking down. But the navigation receiver, in addition to doing navigation, it also measures the signal strength of the direct signal. And from that we can derive the effective isotropic radiated power, or EIRP, of the GPS signal. The EIRP is the product of the transmit power and the antenna gain, the transmit antenna gain. We do this because the GPS EIRP, and in particular the transmit power, is not constant. It's intentionally varied over time, and you can see that on the map on the right. This is an average, weekly average of the transmitted GPS EIRP, and you can see that in general the power is higher in the most of the eastern hemisphere, and then lower in most of the western hemisphere. And if you zoom in on transition zones, so this region right in here, when the GPS power is increased from a low power to a high power, and then another transition zone over here as it leaves Eastern Asia from high to a low power, there are these events called flex power events, and these are the times at which the power is changed on board, the transmit power. And this is zooming in on one of those flex power events right here. This dashed line is the power received by our zenith antenna. So this is the zenith navigation receiver, and you can see that the power is lower here, and then over a very short period of time, this is about a 30-second period of time, the power goes up by quite a bit. And if you don't compensate for this or correct for this change in power, then you'll mistakenly think that the scattering cross-section of the surface has changed. And we didn't realize that this was a significant problem early on in the mission. So in our early data products, version 2.1, we did not compensate for changes in transmit power. And that's the reason why this scattering cross-section, the red line, looks like it goes up much higher, because actually the transmit power went up. We now have a way to automatically, dynamically track the transmit power and correct for it in our level 1 calibration, and that's the version 3.0 algorithm we're using now. And the result of that is a consistent, steady scattering cross-section before and after the flex power event. There's this little blackout region here right when the power is changing quickly, when we don't try to do the correction because things are changing so quickly. So we have a quality control flag that looks at the rate of change of the EIRP and flags data if it's changing too quickly. Anyway, I just wanted to point this out because this is an important consideration for accurate calibration in the two hemispheres, and in particular for calibration right in these transition zones here and here. And in terms of monitoring typhoons, this would be a typical region right in here where typhoons would be, making landfall on Eastern Asia, so it's important for your application. Here's some examples of measurements by Cygnus of hurricanes, in this case Hurricane Dorian. These are measurements made about 12 hours apart. This is an ascending pass by the constellation, and then descending, and then ascending again the next day. These are 1 hourly measurements, our standard level 3 product. And then these are 3-hour products where we've used the storm-centric gridding that I mentioned earlier in order to sharpen the storm structure. And you can see, for example, in this lower right picture here, the high winds in the storm center and then the radial decay of the winds as you move away from it. We've taken these winds and have done preliminary assessments of the impact of the Cygnus winds on hurricane forecast skill using a numerical forecast model, in this case the HWRF model. That's the operational model used by the National Weather Service here in the United States. And an example of an OSE study using the data is shown here. On the left, this is the prediction of the winds at 3-kilometer altitude by the HWRF forecast system. This is the control when there's no Cygnus data used. So this is a 24-hour forecast into the future, 24 hours of what the winds are at 3 kilometers aloft. In the center, this is the same forecast model, but using Cygnus data also assimilated into the forecast. And you can see when you add the Cygnus data that the azimuthal sector of maximum winds has shifted. In this case, the maximum winds are due north, or largely due north of the storm center, whereas there's a shift to the northeast quadrant when you assimilate the Cygnus data. And the thinking is that that shift is caused by information provided by Cygnus surface winds in the storm center about the latent and sensible heat fluxes up into the storm. And we've confirmed this measurement or validated it by comparing it to some in situ measurements or near in situ measurements by a tail Doppler radar in a Hurricane Hunter airplane that flew through the storm at the time of this forecast. And these are the measurements made by the NOAA aircraft of the storm, of the winds at 3 kilometers altitude. And you can see that the direct measurements show this asymmetric shifting in the storm center, or the maximum storm sector into the northeast quadrant, confirming the predictions with the Cygnus data. Another example of the impact of Cygnus winds on hurricane forecasts is this example is Hurricane Michael. These are the standard operational forecasts. This is a forecast of the minimum pressure in the storm. And this forecast was made about 2 days before the rapid intensification phase. So this black line, the best track measurement of storm center minimum pressure, is what actually happened. And you can see this steep intensification of the storm, drop in the minimum surface pressure. The red line is the operational forecast made by the National Weather Service, and you can see they missed most of this rapid intensification. We then ran the HWRF model again using Cygnus winds, or including Cygnus winds, and you can see that it does a much better job of capturing the rapid intensification phase here when Cygnus winds are included. Again, we think because Cygnus is adding information about the heat fluxes up from the surface in the inner core. I want to shift now and talk a little bit about scattering from smooth surfaces, and in particular over land from inland water bodies. So almost all of the time over the ocean, the scattering is incoherent because the surface is significantly rough relative to the GPS wavelength of 19 centimeters. And when the surface is rough, two important things characterize the scattering properties. One is the spatial resolution of the measurements is determined by the range gating, or the delay, the time delay, and also by the Doppler filters. And that gives you a spatial resolution of about 10 kilometers instantaneous, and it varies somewhat with incidence angle. The other property of incoherent scattering is that the received power, the power received by the Cygnus satellites, is proportional to this product of the ranges. Range A is the distance from the transmitter to the surface. Range B is the distance from the surface to the receiver, and it's this product that determines the proportionality, or the beam spreading from propagation. With coherent scattering, if the surface is very smooth relative to a wavelength, two important things change. One of them is the spatial resolution is no longer determined by the delay and Doppler filters. Instead, it's determined by the first Fresnel zone of the reflection. And for the Cygnus measurement geometry, that's typically between 500 meters and a kilometer, depending on the incidence angle. Another important difference is the range dependence. The range dependence is fundamentally different with a coherent scattering. It's proportional to this relationship here, the square of the sums of the ranges rather than the products of the squares of the ranges. And if you plug in the numbers for the ranges for Cygnus, the difference between these two is approximately a factor of 1,000 to 2,000. So the coherent scattered signal is much, much stronger, 30 to 33 dB stronger than incoherent, and that has a huge impact on our ability to image small inland water bodies. And I have a few examples of that here. This is an image of a section of the Amazon River made by a passive microwave instrument, SMAP, at almost the same wavelength as Cygnus. The SMAP passive microwave radiometer has a resolution of about 30 kilometers. And so this is a 30-kilometer resolved image of this section of the Amazon River. The SMAP active radar also operates at about the same wavelength, and it has a resolution of 3 kilometers. You can see that the sections of the river are much more finely resolved with the 3-kilometer radar than with the 30-kilometer radiometer. And then finally, when Cygnus measures the same section of the river, you get this image here, and you can see that the spatial resolution is much, much better than either the radiometer at 30 kilometers or the radar at 3 kilometers, all these small tributaries and so on. And again, the reason for this is twofold. One, the resolution is set by the first Fresnel zone, not the Doppler filters, and the other is that the signal strength is so much stronger because it's coherent that we're able to resolve small water features that are even smaller than the native resolution of the image. An example of an application of this capability is shown here. These are reflectivity measurements made by Cygnus. So these are Cygnus images just before landfall by Hurricane Isaias in July, and then this is just after landfall in August of 2020. And you can't really see that much difference between these two, but if you take the difference between these two images, you get this image here. So this is the difference between before landfall and after landfall, land reflectivity. And this region right in here we'll zoom in on, and you can see very strong features in the difference. In particular, this region here and this region here in the Dominican Republic. And there was a very significant amount of flooding when the hurricane made landfall in this region and this region, and the flooding caused a lot of standing water, and the standing water supported coherent reflections, and that's why we're able to image the floods after landfall with resolution. Some other examples of inland water body measurements. These are measurements made by Cygnus of South America, and you can see a lot of the water features there. These are images, an image made by Cygnus of Southeast Asia and parts of Africa, and you can again see the strong reflections from standing water. One comment about this region right in here in the Himalayas is kind of blacked out here, and that's because this was an earlier version of our data processing for which the range gating or the delay component of the delay Doppler maps was not sufficient to be able to image these very high altitudes. We've changed the processing since this image was made, and we're now able to properly image the DDMs at the shorter delays that happen at very high altitudes. And that's something, if you have an interest in making measurements away from sea level at high altitudes, you should think about how the delay the domain of the delay component of the delay Doppler map. Finally, also over land, in addition to imaging inland water bodies, we're also able to measure soil moisture because of the effect of the moisture on the dielectric properties of the surface, which in turn affects the reflectivity of the surface. And this is an example of our level 3 data product that we're now producing every day of soil moisture. This is a daily product from the Cygnus level 1 land reflectivities. Finally, in summary, Cygnus was launched in December 2016, originally to study hurricanes and inner core winds to support forecast skill improvement, but And we've taken those winds, and as I've shown you, there's preliminary evidence that the surface winds, when assimilated into a numerical forecast model, do add value and skill to the forecasts. We've also spent time looking at other applications, both over ocean and land, and we've found, in particular with the coherent scattering over land, that there's a lot of other things that you can do with Cygnus data. And then finally, all 8 spacecraft, they were launched in 2016, but they're still working fine. The GPS receivers are working fine. The performance is nominal, and we continue to produce data products every day. Thank you very much.
Thank you for Professor Ruf's presentation. I think we still have some minutes for questions. Any questions?
My question is, you say the Cygnus data has been assimilated to the numerical forecast model. Is that in the NOAA's model or?
Actually, I have the one question for Professor. For the Cygnus, do you still plan to operate it? I think you still plan to operate it, but how much longer you plan to operate it? Thank you for the answers. Okay, anyone else? Question?
Okay, so Professor Ruf, there's a question from Professor Dagang Ye, and his question is, could you please give some comments about the accuracy of the soil moisture of the level 2 products? Yeah, it seems that there's a really like a great deal of work about the rapid change of the GPS transmitter power. And so my question is, so for the Cygnus team, so far what you are working on is monitor the change of the power. Is there any particular pattern or rule, for example, related to the features of the land and ocean, or is there some kind of things that we can do to prepare it beforehand? Thank you.
Yes, there's a number of very consistent patterns, but they're not 100% consistent, unfortunately. But so each of the different block types, you know, there's a number of different generations of the design of the GPS satellites, the different block types, and each of them has their own distinct pattern for changing the power, the transmit power. So you need to characterize them individually, the different spacecraft, GPS spacecraft. In general, they increase their power when they move across the eastern part of the Atlantic Ocean and enter Europe. And then the power is high across Europe and Asia, and then it decreases when it enters the western part of the Pacific Ocean. That's the typical pattern, but exactly when the transition happens from low power to high power and then from high back to low is slightly different with the different satellites.
So for us, the easiest way to address it, well, I don't know if it was easy, but it's what we're doing, is to directly monitor the change in power rather than characterizing the pattern.
Okay, thank you very much.
I hear about the US side. They plan for the next phase of GNSS-R mission. Can Chris talk about the status and the brief of the planning?
Sure. So there are several new missions coming up. One of them is a private company, Spire Global, and they have flown 2 different versions of a GNSS-R satellite. The first one was launched in December 2019, and then they have a new version with better performance that was launched in January 2021. And they have shown some data from the satellites at some conferences, public conferences. And I don't think there's any publications yet, but I'm sure they're working on it. And they have some wind speed science data, level 2 wind speed science data product that they're producing now. And so that's a private US development. And then there's a new mission that was just confirmed in, I think, in November 2020 by the European Space Agency, a new GNSS-R mission called Hydro-GNSS. And it has it's a improved version of the Cygnus receiver built by the same company that built the Cygnus receiver. That's Surrey Satellite Technology, SSTL, in the UK. And I think it has both GPS and Galileo channels on it. Also 4 channels like Cygnus. So yeah, so the Triton will have more channels. So that's good. And then at the University of Michigan, we have been developing a new version of the Cygnus receiver with better capabilities. Also GPS and Galileo, L1 and L5, E1 and E5, with 20 parallel channels, 20 parallel DDMs. And that receiver just finished the TRL-6 environmental testing just last week. It's just finished. And we don't have a satellite mission for it yet, but we have some options, some possibilities, and some proposals, and we'll see what happens. We also have a program starting in August of 2021 where we will take one of these new receivers that we just finished last week, and we will install it on a commercial airline in New Zealand. The Air New Zealand commercial airline is a partnership between NASA and the New Zealand Space Agency. And we will install it on this commercial airplane permanently. And when the plane is flying, it will automatically record data, reflection data, and then direct data with a GPS antenna on the top of the airplane. And then when the plane lands in the, at the airports, it will automatically transmit the data back to Michigan. And this will be continue on for several years. So we'll have lots of new measurements over both land and ocean with the New Zealand airplane. And that's to do a lot of, testing of this new receiver technology, and also to do more of the science measurements from the aircraft. So those are the new programs happening.
Thank you very much.
Hello, this is JJ Miao. Could I ask a question from NCKU?
Yes, please go ahead.
Yes, maybe it's a question follow-up questions about these new missions. Okay, Professor Ruf mentioned. May I ask what's the spatial resolution, or we call it the spec of these sensors, GNSS-R sensors, okay, in the future missions, okay, and how this spec could be improved, I mean, in the future, okay, in terms of this technology development.
The spatial resolution is, you know, for incoherent scattered signals, for rough surfaces like the ocean, it's determined by the Woodward ambiguity function, right? The lag correlation of the PRN code. And so with the Cygnus L1 CA code, the resolution is, you know, approximately 15 kilometers. It varies a little with incidence angle. But if you use that L1 CA signal, then the resolution will not change. It's fixed by the code length, the code behavior. The L5 signal and the E5 Galileo signal have significantly wider bandwidth. So the ambiguity function, the autocorrelation function, is much narrower because it's inversely proportional to the bandwidth. And those have quite a bit better spatial resolution, 3 to 5 kilometers, depending on the incidence angle, also depending on the orbit altitude, but approximately 3 to 5 kilometers with the L5 signal. And that was the main reason why we added L5 and E5 capability to our new receiver design. Because the bandwidth is much wider, it requires a much faster processor, a faster digitizer, and more, you know, digital signal bandwidth in the processor. So that's a technology concern that we had to accept to get the improved performance. And those numbers, you know, 15 kilometers for L1 or E1 and 3 to 5 kilometers for L5 or E5, those are numbers appropriate for rough surface incoherent scattering. For coherent scattering, the resolution is much finer, you know, approximately 500 meters.
Okay, thank you. Thank you very much. Yeah.
Yes.
Maybe Chris can help to answer the question that he mentioned about there's a uncertainty in when determining the specular point over land. So I wonder that, for example, for the case in Taiwan, we actually have complex terrain and also land surface type. So can you comment about, for example, we have very rapid change of, for example, high mountain and also land, and also we have pond. So in that kind of in this kind of situation, do you think that it will highly increase the difficulty for soil moisture estimation or the related application? Thank you very much.
Yeah, the determination of the geolocation of the specular point is much more challenging when the terrain is not smooth, when there's, you know, rapid changes in elevation over a short period of time, like in the mountains. And you know, Mohammed Al-Khaldi showed in his presentation a map of the confidence in the determination of the specular point, and the confidence is much lower when the mountains are steep, and that confidence map is derived from the behavior of the first and second derivative of the elevation. And that maps into confidence in the specular point solver, the geolocation determination. So, you know, if the altitude is high, but it changes fairly slowly. So the you know, the derivative of the height is fairly low. Then you still have good confidence in the location, but sometimes you don't. There's some very interesting animations that Dr. Alcalde and Scott Gleason have made, and also other people on the team, looking at the behavior of the DDM as the specular point track crosses over major mountain ranges, the Rocky Mountains in the United States, or the Himalayas in Asia, or the Andes in South America. And the specular point moves around quite a bit in the DDM as it crosses through the mountains. And there's a number of places in the DDM where you will see more than one specular point when the terrain is rough enough. So in that case, it's not even there isn't a single specular point, you know, because of just the shape of the terrain. And so yeah, it becomes much more complicated. And when the surface roughness statistics are, you know, if the surface is rough enough that the specular point solver has a lot of trouble, I think it will probably be much more difficult to determine the soil moisture. That was your other question. Yeah, I mean, it's even difficult to determine where the specular point is in that case. Yeah, things are much more simple when the surface is smooth. There's a single specular point. It's well defined where it is. It's the same location as the point with minimum propagation path, right? The specular point and the minimum delay are the same location usually in the delay Doppler map. But in rough terrain, that's not true. So even the definition of specular point becomes more complicated when the surface is rough, because, you know, one location will have the minimum delay and a different location will have the strongest signal if the side of the mountain is tilted in the right angle.
Thank you. I also have one more question. Is that okay? Yeah, I have the question about the application for the numerical weather prediction. And Chris showed this very nice result and example of how assimilating sickness wind speed data can improve the hurricane prediction. My question is, I mean, with our experiment, because we are using the ensemble-based data assimilation system, what we often see is that the wind speed data alone actually can degrade the wind direction correction. So that also suggests that we also need at least some good quality of the wind direction estimation in order to really bring up the benefit of the sickness wind speed data. So I guess my question is two. First is that so should we expect that there will be more in terms of algorithm, including the wind direction information will be coming in the future? And the second thing is that in terms of the suggestions, what do you think about how to improve this part for improving the wind analysis field for the numerical model for weather prediction? Yes.
Right. So there's several different groups on the Cygnus Science team independently working on numerical forecast models for hurricanes and assimilating Cygnus data. And they have different approaches that they're using. And one of the groups, this is the group directly affiliated with the NOAA Hurricane Research Division in Florida. They are using a variational assimilation method which uses a priori information about wind direction from other sources, and they merge it with the scalar wind speed from Cygnus. And in their case, and they use the Cygnus winds as a constraint on their other wind information. And in their case, the fact that, well, I should back up a little. The Cygnus, or just GNSS-R measurements in general, are very insensitive to wind direction. Both that's been demonstrated empirically and also demonstrated with just rough surface scattering theory, that there's very little sensitivity to the wind direction, much less so than with monostatic scatterometer or backscatter measurements, where there's a strong wind direction sensitivity. So if you were interested in measuring wind direction, that's a bad thing. But if you're interested in measuring wind speed that is not sensitive to wind direction, it's a good thing. And so they're trying to make use of that property, that the wind speed measured by Cygnus is not affected by the direction, to use the wind speed by Cygnus as a constraint on their other wind products, for which they have the direction, and they have, you know, some you know, ambiguous solutions for the wind speed. You know, with standard scatterometer winds, there's wind speed ambiguities, or rather wind vector ambiguities, and this helps to remove those by putting a constraint on the wind speed. Anyway, so there's a group that's you know, specifically focusing on the use of Cygnus scalar wind as a constraint on their wind vector, and they've had success with this in terms of forecast skill impact. There'll be a session. We have a Cygnus science team meeting scheduled for the last week of July, and it will be I think it will be a hybrid meeting. Some people will be coming in person to the meeting, and probably most of the people will still be coming by virtual. And so it'll be very easy to attend virtually. So if you're interested, you're certainly invited to attend the meeting, and there'll be probably one half of one day will be dedicated to the hurricane forecast data assimilation methods and the progress by the different groups on the team, and that would be a good time to get up to date information from the different groups working on this.
Thank you very much.
Any question else? Okay, if there's no any question else, I should hand over the meeting to Professor Yang.
Yeah, thank you.